Okay, so 6:11, the average time for 18 to 24-year-olds watching video on their smartphones. View is 174 minutes per month. It's a normal distribution. Sigma is 15 minutes per month. So in part D, you were asked 1% of the population spends less than how many minutes watching videos on their smartphones. So here, we know what the distribution looks like. We're looking for this value of x such that the area here is 0.01. Well, then the area to the right is 0.99. From the table, we know this is going to be a negative value of z because the mean of 0, the area to the left is 50%, 0.01 is a lot less than 0.5, so this is going to have to be on the negative side of the z-axis. So we look in the table, the left side of the table, for the area in the body of the table. This is the reverse problem. We're looking for z instead of, we're looking for z instead of given a value of z, looking for the area. Here we have the area, so we look up in the body of the table, the area that's closest to 0.01. So we're looking here, and we find that the probability that z is less than negative 2.33 is approximately 0.01. So, any questions about how we find that from the table? All right, well, z is x minus mu over sigma. So the probability that x minus mu over sigma is less than minus 2.33 is approximately 0.01. So I can set x minus mu over sigma equal to minus 2.33. I know mu, I know sigma, I can solve for x. So I have x minus 174 over 15 equals minus 2.33. Multiply both sides by 15, add 174 to both sides, and we'll get x equals 139.05 minutes. So that's the cutoff. Less than 1% watch videos on their phones less than 139.05 minutes. 99% watch videos on their phone for more than 139 minutes per hour. Questions on that? And to do that using Excel, so we set up a spreadsheet. Mu is 174, sigma is 15. This we looked at last time for parts A, B, and C. For A, B, and C. For part D, where we're looking for the inverse, the value of x, such that the probability that the time spent is less than x equals 0.01, we use norm.inv with the less than probability, the left tail probability, which is 0.01, the mean, 174, the standard deviation, 15. And without going through all the intermediate steps of looking up z, etc., Excel does that for us, and we get 139.1047. And of course, that's a little bit more exact than the value I got of 139.05. Why? Because if you looked at the table, you didn't have exactly 0.01 in the body of the table. The value closest gave you a z of minus 2.33. In fact, if I had an expanded z table where I could find an area z corresponding to exactly an area of 0.01, I would have come up with exactly that from Excel. Questions on that? Okay, then the exponential problems, problem 644, given an exponential distribution with lambda equals 30, what's the probability that the arrival time, and then you were given a bunch of those to find. So, lambda equals 30, the probability that x is less than 0.1, well, we know for the exponential probability, the cumulative probability, it's 1 minus e to the minus lambda times x. So that's 1 minus e to the minus 3, and that's 0.9502. Questions on that? Probability that x is greater than 0.1.
So in exponential, we determine the time for the next event to occur, right?
Right.
So 0.1 is the time for the next event.
Probability that the next arrival in this case
Is 0.1 second or what is it?
isn't it hours?
So
It's just 30. Yeah, what's the probability that the arrival time is less than 0.1 of whatever the units are? In other words, and they're not giving you any of that, but we assume it's the same units, all right? If it's 30 per hour on average, what we're asking here is what's the probability that the next arrival will occur within 1/10 of an hour? Okay, so 6 minutes. All right, what about the probability that x is greater than 0.1? 1 minus this, so that's going to be 0.049. Probability that x is between 0.1 and 0.2, well, same thing we do in a normal distribution. We take the area to the left of 0.2, we subtract off the area to the left of 0.1, and that's the probability that we want. So it's going to be the probability that x is less than 0.2 minus the probability that x is less than 0.1. All right, so is everybody clear on that? That's the same thing we did with the normal. It's another continuous distribution. So the probability that x is less than 0.2 is 1 minus e to the minus 30 times 0.2. And the probability that x is less than 0.1 we already calculated is 0.9502. So this turns out to be 0.9975 minus 0.9502, and that's 0.0473. Questions on that? And part D, what's the probability that x is less than 0.1 or greater than 0.2? So now we're looking for the area not equal to this, less than 0.1 or greater than 0.2 is this area plus this area, but it's a continuous probability distribution. I know the entire area under the curve is 1. I know this area is 0.0473. So if I take 1 minus 0.0473, which gives me 0.9527, that's the probability that x is less than 0.1 or greater than 0.2. And of course, you could have calculated that directly. The probability that x is less than 0.1, we know is 0.9502. The probability that x is greater than 0.2 is going to be 1 minus 0.9975. And that'll give you the same result. Any questions on that one? Okay, problem 650, I asked you to solve using Excel. 650. The time between unplanned shutdowns of a power plant has an exponential distribution with a mean of 20 days. So lambda is 20. Find the probability that the time between two unplanned shutdowns is less than 14, more than 21, less than 7. All right, so let's look at what we do in the Excel. All right, so I'm sorry, and what I said when I was reading this was wrong. The time between unplanned shutdowns has a mean of 20 days. That's not lambda. What is that? Lambda is a rate. Lambda is going to be number of unplanned shutdowns per day, not average time between shutdowns. So what are they giving you? What value are they giving you? What's the 20? Days. How do you find lambda? Yeah.
1 over lambda?
1 over lambda. 1 over lambda is the time between events. So if they're giving you the average number of events, I'm sorry, if they're giving you the average time between events, that's 1 over lambda. Lambda is 1 over 20. So 1 over lambda is 20, lambda is 1 over 20, or 0.05 unplanned shutdowns per day. So you gotta be very careful about the units in the exponential, well, anytime, but in this case, in the exponential distributions. So, probability that x is less than 14, we said we can use the exponential distribution, exponent.dis, and this is x, this is lambda, sorry, this is lambda, which I have in cell C3, and since it's a cumulative distribution, it's a continuous distribution, we're looking for the probability that x is less than 14, so I use true. What's the probability that x equals exactly 14? 0, good.
So wait, can you, what is A, the actual answer that you're getting?
I haven't gotten to it yet. We're in the middle of it. Okay, so are there any questions about the formula that we're using, how we got lambda and the formula? Okay, so the probability that x is less than 14 is going to be this number, which turns out to be 0.5034. All right, so it tells us 14 is about the mean, approximately number of days. Probability that x is greater than 21. Well, Excel is giving me the less than probability, so if I want the greater than probability, I have to take 1 minus the value that Excel will give me. So that's 1 minus exponent.dist, x is 21, lambda 0.05, and true. And that turns out to be 0.3499. And probability that x is less than 7, that the time between two unplanned shutdowns is less than a week, is same as part A, but x is 7 this time. And that turns out to be 0.2953. Questions on that? And then I asked you to do 7.2 and 7.7, right? Okay. 47.2, you're told the mean is 50, standard deviation is 5, it's a normal distribution. We take a sample of size 100, and we want to know if we calculate the mean value of this sample of x's, what's the probability that that mean value is less than 47? So we're going to use the normal distribution because the central limit theorem tells us if we don't even need the central limit theorem. In this case, you were told the individual values were distributed normally, so we know that the sampling distribution is normal. The distribution of x bar values will also be normal. But the distribution of x bar values has the same mean as the distribution of the individual values, 50, but it has a different standard deviation. The sampling distribution has a smaller standard deviation, sigma sub x bar, which we call the standard error of the mean, and it's equal to sigma over the square root of n, which is 5 over square root of 100, or 5 over 10, or 0.5. So the sampling distribution has a much smaller standard deviation than the individual values. It always has a smaller standard deviation. We're always dividing by a number bigger than 1. So the probability that x bar is less than 47, well, we have to change this to a z value. But when we're talking about the distribution of x bar, the z value is x bar minus mu over sigma sub x bar. In other words, it's the standard deviation of whatever characteristic we're measuring. When it's x, it's just divided by sigma. When it's x bar, we need to divide by the standard deviation of the x bar distribution, which is sigma x bar. So that's going to be the probability that z is less than 47 minus the mean divided by the standard error, sigma sub x bar. And that's the probability that z is less than minus 6. That's what we're looking for. If you look at the table, you see that what happens? It's 0. It's 0. Questions on that? Probability that x bar is between 47 and 49.5. So now I'm looking for an interval under the normal curve. I'm going to have to find the two z values and then subtract the area to the left of the bigger one from the area to the left of the smaller one. So that's the probability that 47 minus 50 over 0.5 is less than z is less than 49.5 minus 50 over 0.5. And that turns out to be the probability that z is between minus 6 and minus 1. So that's the area I'm looking for. So I'm going to take the area to the left of minus 1, which I find right from the table. I just look up a z of minus 1.00 in the left side of the normal curve, and that turns out to be 0.1587 minus the area to the left of 0. Well, we already found out that was 0, so it's 0.1587 for the probability that x bar is between 47 and 49. And part C, the probability that x bar is greater than 51.1. probability that z is greater than 51.1 minus the mean divided by the standard error. And that's the probability that z is greater than 2.2. So that's the area to the right of 2.2 under the standard normal curve. The table gives me areas to the left of z. I look up the area to the left and I subtract from 1. So that's going to be 1 minus 0.9861 or 0.0139 for part C. Questions on that? And 7.7, time spent on tumblers distributed normally with a mean of 28 minutes, a standard deviation of 5 minutes. We take a sample of n equals 25, and we want to find same computations. All right, so mu is 28, sigma is 5, n is 25. So sigma sub x bar, since all the questions are about probabilities associated with x bar, the sample mean when I take a sample of 25, sigma x bar is sigma over the square root of n, or 1. So, probability part A, x bar is between 27.5 and 28.5. Same thing we did in the other problem. So it's the probability 27.5 minus the mean of 28 divided by the standard error of 1 is less than z, less than 28.5 minus 28 over 1. So in all of these problems, you see that we're doing the same thing we did with our discussion of the normal distribution, but because we're talking about the sampling distribution, we're dealing with x bar and with sigma sub x bar, right? So this is the probability that z is between minus 0.5 and plus 0.5. So we're looking for that interval. We take the area to the left of 0.5, which is 0.6915, minus the area to the left of negative 0.5, which is 0.3085, and that's 0.3830. Any questions on any of these steps, on how we get any of these
The
numbers?
6915, so that was taking 28.5 minus 28, right? And then to the,
No, that was,
Yeah.
the minus 0.5, is that what you asked about?
That's about the 600.
Oh, no, the 6.9, yes,
so then
28.5.
it's 0.5 over 1, right?
Yeah.
Yeah, which is 0.5, that's this point,
0.5.
why don't you look up here, that's this 0.5,
Yep.
okay.
And then when I went into my book, I saw that equals 0.9999.
No.
A z value of 0.5? We're looking, you should be looking
You
at
look
the
5,
table,
25.
here's the table.
Yeah.
0.0, 0.1, up to 6.0.
You go to the 0.5, it's 0.6915.
Oh, you're absolutely right, that's exactly what I did.
Okay,
Genius.
any other questions? Okay. Part B,
Thanks, Jim.
probability that x bar is between 27 and 29. So we do the same thing, 27 minus 28 over 1, and 29 minus 28 over 1, and that's the probability that z is between minus 1 and 1. So the area to the left of 1 is 0.8413, the area to the left of -1, 0.1587.
I'm not gonna waste this.
So that probability is 0.6826. Which you could have gotten without looking at the normal table at all. How? How could you have gotten the answer to this? That number should look familiar. Not, this is a normal distribution. When we know it's a normal distribution, we don't use the empirical rule at all. The empirical rule is less precise than the normal distribution table. All right, so no, it's not from the empirical rule, although it happens that the empirical rule does give us the same information. But we know it's normal. We don't need the empirical rule. What do we know about these two numbers? Well, if the mean is 28 and the standard error is 1, isn't this the probability that we are within 1 standard deviation of the mean?
Yes.
For a normal distribution, the probability of being within 1 standard deviation of the mean is 0.6826. The probability of being within 2 standard deviations of the mean is 0.9544. The probability of being within 3 standard deviations of the mean is 0.9973. All right, those are values that you should be familiar with. And in this case, of course, we got the same thing. Z is between 1 standard deviation below the mean and 1 standard deviation above the mean. All right, but you could have recognized that right up here. Yes?
On page 197 in the book, it keeps telling us to, when this happens, it's telling us to refer to the empirical in normal distribution. That's why I think.
Wait, the empirical normal distribution is not the same thing. What page are you talking about? Page 97, 197?
Seven at the bottom. 197.
Okay, the result is the justification for the empirical rule. In other words, we're using the normal distribution, and we can use that information in the empirical rule. The empirical rule is a weaker rule. It doesn't say we're not using the empirical rule to calculate a normal probability, it's the reverse. All right, the empirical rule is a weaker rule. The empirical rule just requires that it's approximately symmetric. It doesn't require that it's precisely a normal distribution. When you know that it's precisely a normal distribution, you use the normal table. All right, what they're explaining there is where the empirical rule probabilities come from. What does the empirical rule say? It's about 2/3. It's about, in fact, 68.26%. 2 standard deviations, about 95%. 3 standard deviations, 98 to 100%. All right, that's a weaker statement than knowing that you have a normal distribution. So that's what they're referring to, that you can use the information about the normal to talk about the empirical rule. They're not saying the reverse, that you use the empirical rule to calculate normal probabilities, okay? All right, that was B. C, if n equals 100, solve part A. So what happens if n equals 100? What changes?
Sigma.
Yeah, sigma x bar. So now for n equals 100, sigma x bar is 5/10 or 0.5. You have a bigger sample, you have more information, you have less variability. You have a smaller standard error. All right, so that's all consistent. Now, what about the probability? Well, now we're going to calculate the probability that 27.5 minus 28 over 0.5 is less than Z is less than 28.5 minus 28 over 0.5. That's the probability that Z is between -1 and +1, which we already know is 0.6826. Here, it was 0.3830. What's happening? much more of your data, of your X bar values are centered around the mean. It's a smaller variation, a smaller standard error. So they're not spread out as far. The probability of being close to the mean in that case is much higher, because you have that lower variability, you have a narrower, higher distribution. So in part D, they ask you to explain, because n is larger, your variability is smaller, sigma sub x bar is smaller, you have less dispersion, more information, more certainty, so more of the sample means are closer to mean. Any questions on that?
Yeah, can you go through the explanation of D real quick again?
What I just said?
Yeah, just a lot of the things that are.
When you
coming
have
out of the way.
a larger sample size, you have more information. When you have more information, you have more certainty.
No, I understand that.
So what's the question?
Just kind of like how, if we were, so, yeah, I'll tell you right. I said, the larger sample size decreased the standard deviation, creating more probability around the mean. Like, would that be acceptable on that?
That's basically right. Yeah, the whole idea is that you need to remember that the more information you have, the more certainty you have. The more your values will be clustered around the mean, but less variability. So all of these measures are very consistent. All right, any other questions? Okay, so let's take a break now, and when we come back, we'll get back